Perfect. We are recording, and what I'll do is what we discussed last week. We'll go through the Shear chapter basically very quickly, and then we can do the exam or the in-class problem that we discussed last week. I'll go through the solution procedure for that, and then we're going to switch to torsion. Okay. So, yeah, let's skip this initial part. So for torsion, we eventually came up with the equation for an asymmetrical loading or asymmetrical cross-section and with multiple shear force acting at it. We got the equation that basically stated the shear flow Q can be defined by minus and then Sx Ixx minus Sy Ixy divided by Ixx Iyy minus Ixy squared, and then the integral of 0 to s tx ds, and similarly for 0 to s to ty ds. Please note that here we have shear force on x and shear force on y, and here we have shear force on y and shear force on x. That's basically the only thing that changes. And also the moment of inertia, here is xx by y. So, and then we said, of course, we have again a symmetry problem. That means that our moment of inertia on xy is equal to 0. So it simplifies our problem. And then, of course, if we have only given one shear force, say Sx or Sy, then subsequently it reduces even more in complexity. So the key point was like, okay, how do we determine, so the Sx is the shear force that's often given, Iyy, Ixx are the moment of inertia, so that's relatively easy to calculate. So the trick here is, and the difficulty lies in basically evaluating that integral of tx ds. So we multiply by the thickness for the sections, and then we do the integral of 0 to s x ds. So the thickness is a constant, so we can take that out. But the x, the s part can be a variable, and y ds can also be a variable. So the 0 to s, that's our segment that we travel over. So that's the path the shear flow basically flows along. So we have to come up with the x value as function of our path s. So if you look at this problem, if you go from point 1 to point 2, we travel a total of 0 to h over 2. So our bound of 0 to s, in this case, s will be equal to h over 2. That's the total distance of the segment that we travel. So then the question becomes, how does x vary over that segment of 0 to s, over that segment 1 to 2? So we can see that the segment, the x location, varies if we vary along the segment s. Because of that, we have to basically define what x is a function of s. And in that case, we can easily define it as minus h over 2 plus s1, which s1 is 0 to h over 2. So you can do that for all the different segments. Then you can fill in the equations, you can do the integral, and then you basically get a formula that's basically as function of x and y, or a function of s, and then you can evaluate it at locations 1, 2, 3, and 4. So that was for open sections. And then, of course, you can plot it as well. So the second topic we discussed was the shear center. Like, if you apply the shear force at the location at your cross section, depending on where that location is, your structure will bend and twist. However, if you apply it at a certain location, your structure will only bend. That location is known as the shear center. Basically, it reduces the coupling between bending and twisting, or neglects that. So an idea for the shear center is we calculate that by doing a moment equation. So we calculate, and before, so yeah. So an easy way to find the moment of inertia is actually looking at the geometry of your cross section and drawing the lines of your shear flows and finding if there's a common point in which all the shear flows flow through. If you can find such a common point, then by definition your shear center lies at that common place. So, and with that said, if you cannot find such a common place or common location, what you have to do is come up with the moment equation and set that equal to 0. So you basically say the moments created by the shear force around the point is equal to the moments created by the shear flows around that same point. And doing so, you can find, you can define an equation basic moment equilibrium equation, and you can solve for that unknown variable, which is the arm of your shear force with respect to that point, and you find your shear force location, shear center location. And then the next topic we discussed was what we can do with a closed section, because in open section we always said we're going to start a location like 1 or 4 because we know that the shear flow at that location is 0, so we can start our equations. So for closed section, we don't have a location where we know the shear flow be 0, so we have to start at a different location. What we do is we basically make a cut in this cross section, basically convert it from a closed section to an open section, and then we say because of the cut, we have to make a correction shear flow added to it as well. So the whole closed section is basically make a cut, solve it as an open section, and add a correction shear flow of QS0 to it. And to define that correction shear flow, we know it's a constant shear flow, and by just looking at the geometry of the problem and taking an arbitrary shape, and we do some mathematics. So we do the integral of it and the moment arm, and along the path that basically flows, we can define that this open shear, the correction shear flow, the contribution is the moment contribution of the the correction shear flow is equal to 2 times the enclosed area multiplied by correction shear flow. And in this manner, now we have basically one equation, one unknown, which is the correction shear flow, and we can solve for the correction shear flow. And you often pick a moment. You want to take the moments, pick a location where you want to take the moments around that is basically convenient for you. So you want to take it at the location at which both shear forces go through, because then they don't have a moment arm and become 0, or a location where most of the shear flows go through, because then you can ignore those shear flows contributions. And we did a small example. We found this the correction shear flow, and once you find the correction shear flows, you basically add that to the existing shear flows to get the final shear flows out of it and the final values of those shear flows. And we say that as well, there's no negative shear flow. That basically the negative sign implies that the direction you chose or you defined your shear flow to be in is opposite of that direction. And this last thing that we discussed was what happens if we have a closed and open section. So we had this problem on the slides, and we said, go do this at home, and we can go through it in this lecture. So what we said is for this problem, we're going to tackle it is we're going to start at the open section, and then we're going to go through the closed section, and we're going to make the cut and go from there onwards. So let me see. So we're going to focus back on our whiteboard. So let's see what the dimensions were. So we have a bunch of coordinates given already. So 1, 2, 3, 4, 5, 6, 7, 8. And our axis system goes in the middle. And see, this is our x-axis, this is our y-axis, and our shear force also acts on our y-axis. And we define this point here in the middle as O or 0, and we define this middle point between 5 and 4 as 0.9. So if you look at the dimensions, this is 100. This is 100 as well, 100 as well. This is 100 as well. And then from the side, this section, which is 100, and then always, this goes to the middle of the section, approximately. So that's 100, and this is 100 as well. So we have all the dimensions. The book gives you the following paths. So this is path S1, this is S2, this is S3, and this is S4. And they define starting here as 5. So those are the different segments defined by the problem. And we're going to continue just using those segments I can show you later on that I will do one segment differently, but the solution is the same at the end. So what do we know about this problem? Okay, so let's analyze it. So we know we have given Sy, but Sx is not given, so we can assume it's equal to 0. We know we have one plane of symmetry, so therefore we can assume, or we can conclude actually, that Ixy is equal to 0. Based on those two equations, we know that our shear flow equation, Qs, is equal to Qb plus Qs0. So we have to go for the closed section because this part is closed, this part is open. So for the open section, we get Qb is equal to minus Sy over Ixx, and to go from 0 to S, Ty ds. And let me see, the thickness is, let me see, what's the thickness? I think the thickness is 2 everywhere. Yeah. So thickness T is equal to 2 millimeters everywhere. Okay. So basically what we now have to do is, if we look at our open/closed sections, what we said is we're going to solve, starting in the open section, we're going to move to how far we can get, and then we can focus on the closed section separately and make it a cut, get a correction shear flow, and continue like that. So for the moment of inertia, what we need to know is where the centroid lies. So normally, if we have a symmetry, we can basically guess where the moment of inertia lies or the centroid lies. But in this case, we have to calculate it because the moment is not doubly symmetric, so it does not lie in the middle, in the center of the cross section, but lies somewhere towards the top. So step one in this case would actually be calculating the y distance for the centroidal axis. We know the x distance will lie on the y-axis somewhere, because based on symmetry, we know that. So what's that? So we know that's equal to summation of area times the y over the summation of areas. So in this case, it doesn't really matter where you calculate from. You can choose your reference points at the bottom or the top. Let's go for the top in this case. So we basically do the summation of area multiplied by the distance from the top over the summation of the total area. So let's start with segment 1, 2. So segment 1, 2, the area is 100 times 2. So we get 100 times 2 because the thickness is everywhere 100. Multiplied by, if we use the top as a reference line, the centroidal point from segment 1, 2 will lie in the middle because it's just a straight line, a rectangular section. So that will be 50 across from the top. Plus this area, that will be 100 times 2 as well. And its centroidal axis will lie here in the middle, but that basically coincides with our y-axis. So that's 0. For this segment, 3.0 is also 0, 0.6 is also 0, and 6.7 is also 0. So I'll ignore those. So those basically will be not included. So we can do the same thing for 7.8. That will be 100. That's basically the same as 1.2. 100 times 2 multiplied by 50. And then we do the same for 3.4, 5.6, and then for 4.9 or 4.5, how you want to see that. Okay, so that ends there. So this is segment 3.4. So that's 200 times 2, 200 times 2. And its centroidal axis lays at 100 from the top, so we multiply by 100. So segment 6.5 is the same as 3.4, so 2 times 100. And then we have segment 4.5, which is centroidal axis lies here. So that's 200 from the way from the top. So we get 100 times 2, multiplied by 200, plus 100 times 2, multiplied by 200. That segment is, so this segment 1, 2, 7, 8, 3, 4, 6, 5, 4, 9, and 9, 5. So that's the top part. So we divide that by the total sum of areas. So that's basically, and now we use symmetry, so the 2 gets basically in front. So 100 times 2 plus, in this case, now we take this into account. So that's 100 times 2 as well, plus 3, 0, 100 times 2, plus 200 times 2, plus 4, 5, 100 times 2. And if you calculate that, you will see that, yeah, let me see, is it correct? One, 2, 3, 4, that's correct. I'm missing 200 times 2. That should be correct. Then we get 75 millimeters from the top. Yeah. 1, 2, 3, 4. I think there's a mistake in this lecture slide, but it should be 75. The end conclusion is correct. So that means our centroidal axis lies at 75 millimeters from the top. So this distance to the centroid, C, is 75 millimeters. And this part is important because we basically have to calculate the moment of inertia around this axis point. Let me see. 100, 100, 100, 200, 100. Okay. So now we can continue and calculate the moment of inertia of this system, knowing that our centroidal axis lies basically at from the top 75 and x is 0.
So when you're finding the centroid, what reference axis did you choose?
I used the top surface as a reference. So let's use the red line. So I use this line, this coordinate as a reference. So in this case, you can say from 0, doesn't matter. It's just from a line from the top.
That basically eliminates the 2, 3.
2, 3, 3, 6, and 6, 7, yes. Those they don't have any contribution because the moment arm is equal to 0. So let's calculate the moment of inertia. So calculate that on this side, Ixx. So what we can do is we just do the moment of inertia as is, and then we translate that with the using Steiner term to the correct axis. So, and we can use symmetry, so we can basically do half of it and then multiply by 2. So this axis, we have 1/12 multiplied by 2 multiplied by 100 to the power of 3. And note that this lies at 50 from the top. So basically there will be an y distance of 25. So you have to multiply by the area, which is 100 times 2 multiplied by 25 squared. So that's segment 1, 2. So segment 2, 3, because it's thin walled, we get basically t to the power of 3, so that one disappears. But the Steiner term is still effective. So in this case, we get 100 times 2 multiplied by 75 squared. Same thing for 3, 3O. And Then we get 3/4. So again, 1/12 multiplied by 2 multiplied by 200 to the power of 3 plus 200 times 2. And its central axis lies at 100. This lies at 75, so it's shifting up 25. So 25 squared is the AD term. And then we get these two axes, 4, 5, which again is just the standard term. So area times 2 multiplied by the distance is 200 minus 75, so 125 squared. So just to make things clear, this is basically the moment of inertia of 1, 2. This is the moment of inertia contribution of 2, 3. This is 0, 3. This is 3, 4. And this is 4, 5. And to be correct, we must multiply this by 2 because we use symmetry. So this is the moment of inertia, and these are all the standard terms, the AD squared terms. So you cannot forget these. See? Don't do it correctly. Yep. Perfect. And if we calculate that, we'll get a number, and that will be equal to 14.5 10 to the power of 6. Since we stated everything in millimeters, we get millimeters to the power of 4. There might be some errors in the solutions in the lecture slides, because some of these dimensions don't add up that I have in the lecture slides. I think the final solutions do add up, but how it's calculated is a bit confusing. Okay, okay, I see what. Okay, so just a heads up, in the lecture slides, what I've done, I've used instead of segment 2, 3, 3, 0, 0, 6, and 6, 7, I've regarded this as one segment of 400 multiplied by 2, and then did the standard term from that. So these are basically added together. Just heads up. But now we can continue because now we have our moment of inertia. We have our shear force is given, so we can do the evaluation of the integral. Okay. So the question is, okay, where do we start? Of course, we're going to start at an open section. So we're going to start at point position 1 or 8. We're going to go from 1 to 2, 2 to 3, and then we're going to cut open the closed section at point 0, and then we're going to go from 0 to 3. We calculate where the total shear flow is at 3, coming from the left and come from the right, and then we go to point 4. So we cannot go to point 3, 4 before we have made the cut and coming in from the right as well. So what we can do to simplify ourselves, I think in the problem is given as 100 kilonewton, so it becomes 100 kilonewtons times 10 to the power of 3. 1 kilonewton, yeah, we go to Newton, so 10 to the power of 3. We divide it by 14.5 10 to the power of 6, and then we get 0 to s ty ds. So what we get is minus 69 10 to the power of minus 4. So it's a bit easier to calculate instead of using sy over ixx. So it's simple. In some cases, it's easy to just plug in the numbers and go out with an easier number to calculate. Yes?
So initially, when we introduced the idea of cutting a section.
Yeah.
So the idea was to get a reference point or a 0 point.
Yes.
So let's say we already have a 0 point at, let's say we start at 1.
Yeah.
Can you not like go from 1 to 2 to 3?
No.
And then
Wait.
use that 3 point to go to 6 and to 4.
No.
That be inaccurate.
So just reiterate. So the question is, can we not just do 1, 2, 2, 3, and then use that 3 point to go to 0 and to 4? So no, because you don't know what the total contribution at point 3 is yet. You have to see it as every intersection you can see as an say an inflow, or so if you have T section, you can see there's a shear flow coming in from this side. So if you go downwards, then you also have a shear flow coming in from that side. So you don't know, you have two unknowns basically in that case. So you need to know where the total shear flows are coming from a 0 point, starting point, before you can continue.
So the idea is to cut the section somewhere where there are intersections. That's it.
So the reason why we cut here is for a couple of reasons. First and foremost is an asymmetry line. Second is if we started 1, we can go to 2, we can go to 3, and then we can start from 0 to 3, and then we can continue. You could make your cut at 9, but then what you have to do is go from 1 to 2, 2 to 3, 9 to 5, 9 to 4, 4 to 3 before you can go 0 from 3 to 0. It's just being a convenient point. You can also make a cut here at 4 and then just go from 4 to 3 and coming in from 1 to 3 and then go and continuing. But we will come up to why we choose that location and why it's useful. So here we get minus 69, 10 to the power minus 4. And then we do the segment. We know we have 0 to S, we get 0 to 100. The t we can take out of it, because that's just multiplied by 2. And then we have to come up with y TDS is. So we know based on the fact that y will change as we move along the segment 1, 2, we have to come up with an equation for that. So from our central axis, so if you look at 1, 2, 1, and 2, and we are centroid here, this is at minus 25 because this was 75, right? And this was 100. And we go to 0, right? No, we go to 75. We go to 75. Just if you would plug in the coordinates. So let's say, so let's plug in coordinate systems. So we get minus 100, comma, minus 25. And this coordinate is minus 100, comma, 75 from your centroidal axis. So we know that our distance goes from 0 to S. So if we start our location, basically you start out from minus 25. If we add S, going from 0 to S, from 0 to 100, then we get our coordinate system. So y is defined as y is equal to minus 25 plus S. Does this make sense? Because this is basically where most of the problems, or most of the inaccuracies will originate. Not being able to find the correct y and x as function of S, or in some cases a constant. So what you can do is just generate the coordinates, know where it's going from 0 to from minus 25 to 75. So you start at, if S is equal to 0, so you must start at minus 25, and then you plug in your S value, and you go from 0 to 100, then you must end at your positive 75. If you end at a different number, then your equations, you did something wrong. Okay? So we know that y is equal to minus 25, well, plus S. So we can plug this in. So minus 25 plus S1, as indicated, ds. So we can take the integral, so we get minus 25s plus S1 over 2 squared. So what we get is minus 69, 10 to the power minus 4. So we get minus 50s I just plug in the 2 to the other, brought it into the brackets, and did the integral, so we get s1 squared, and it goes from 0 to 100. So, and if you evaluate, so we now have to evaluate point 2, so QB2 is equal to QB12 at S is equal to 100. And that's equal to plugging in 100 and evaluating this equation. I would get minus 34.5 Newton millimeter per millimeter. And this will be our starting point from point 2 to point 3. So now we do, so this is QB12, we do QB23. We start at that value of minus 34.5. And we add this value, so it's negative, so it becomes minus 69 10 to the power minus 4. The integral is again 0 to S2, t is 2, and y is y ds. In this case, y, if we move along the segment 2, 3, y remains constant of 75, so y is equal just to 75. So we can plug in, and segment 2, 3 is 100, so we can plug the bond in as well. So 2 times 75. So we can evaluate the integral. So what we get is minus 34.5 minus 104 S2. And then we can fill in again, point 3, QB3 is QB23 at S is equal to 100. And that's filling in 100 here and evaluating it. And then you get it's equal to minus 104. No, minus 138.5 Newton per millimeter. So quick recap. So we did QB12, went to QB23, and now we get at the intersection of 3. We cannot go down because we have to know what contribution is coming in from the right. Yes?
Can you explain because we used initially negative 25 plus S, and then later it was just 75?
Yeah. So for segment 2, 3, so let's evaluate this segment. Let me see. I still have some room here. So I'll evaluate here, right? So we have point 2, point 3, right? So what's this x coordinate? It's minus 100, comma 75, right? So that's your xy coordinate with respect to the centroid. Point 3 is, sorry, this is actually minus 200, but it doesn't matter. So this is minus 100, comma, still 75. That's your xy coordinate. So your y value along segment, so y along segment 2, 3 is a constant. So when you do the integral of y ds, y is a constant, and the value is equal to 75. So you still have your segment 75. The 2 comes from the fact that we have here a t, and that's equal to 2 everywhere. So that's where the 2 comes in. Okay. So, like I said, we have a closed section, so we make a cut, and we start at point 0 and we go to 3. So if we go from point QB03, we basically repeat the same thing as QB12. It's more or less the same thing. And the reason why it's basically the same thing is, well, it's actually more or less the same as 2, 3, but the starting point is equal to 0 and up to negative 34.5. So you can basically argue you only have minus 69 10 to the power minus 4 0 to S3 of T is 2, and Y, in this case, again, a constant, is 75 as well, Y ds. So this becomes minus 104, 1.04 S3. And if you evaluate that at 100, so QB.3 coming in from the left, say coming in from 0, let's call this coming in from 2, so not a subscript 2, there's QB03 evaluated as equal 100, so that's equal to minus 104 Newton per millimeter. So we now also know this segment, QB03. Now we know all the incoming shear flows of 0.3, and we can calculate the outgoing shear flow. So now, and only now, we can calculate segment 3-4. I'll move to that side of the board. I want to keep that as is. So QB3-4. So we have to add in all the starting points. So this was negative 34.5. So that's negative 34.5. Plus starting point from this side, QB03, that was negative 104. So plus negative 104. So we get negative 130. Is that correct? Q3, no, sorry, it was negative 138. So it's on here. So there's one negative 138.5 minus negative 104. So this is basically negative 242.5 plus our regular shear flow. So again, from minus 69 10 to the power 4 minus 4. So this plus becomes a minus because we have minus here. And the integral from 0 to S4, and then Ty ds. Yeah. So again, let's do it on this side. What is Y in segment 3-4? So segment 3-4, Y ranges from plus 75 to minus 125, and it varies a total length of 200. So your Y is equal to 75 minus S4. Yeah. So it's this part, because I want to emphasize on this part of the equation, because this is the most crucial part. This is where you can run. Do you guys understand how to get this to these equations for X and Y? If not, if you want to discuss it later after lectures, please come to me or email me, and then we can go through it in more detail. But in this case, for segment 3-4, we have negative 75. So this becomes negative 242.5 minus 69 10 to the power minus 4. From 0 to 200, 2 times, and then 75 minus S4 ds. So 69 10 to the power minus 4. And this becomes 150 S4 minus S4 squared, and evaluated between 0 and 200. Yeah, it's still readable. So 0.4, we have to evaluate Q4 or QB4 is equal to QB34, and S is equal to 200. So we plug in 200 in this equation, and we can get our number out of it. And if we do this correctly, we get minus 172.5 Newton per millimeter. And the last point that remains is basically going from Q4 to 9. So we can do QB49. That's basically, we start at negative 172.5. 172.5, and then we do minus 69, 10 to the minus 4, 0 to S5. Ty ds, t is equal to 2, y is equal to negative 125, negative 125 ds. So this becomes basically a plus, negative goes, and this 125 becomes a 250. So you get negative 172.5 plus 69 10 to the minus 4, and then 250 S4 evaluated 0 to 100. And if you do this correctly, if you evaluate this QB9 in this case, that's equal to QB49 evaluated at S equal to 100, S equal to 0. Joule should be the same. So in Maxim, what he does, he restarts, once you calculate 0.4, he restarts at 0.5. 0.9. He says, and the reason why he restarts it, he said based on symmetry, if I make a cut, if this is 0, this must be 0 as well, in this case. So then he basically has a second 0 location that he knows the shear flow, and he can calculate going from the left. But you can continue calculating going, say, counterclockwise. So instead of doing 9, 4, you go 9, 4, 9. And you will get that is equal to 0 there.
For 4, 9, we use, is it like 250 or 200?
4, 9 here?
Yeah, above that. So it's 200, yeah.
So no, sorry. We're doing Q49, right? So there's a bit of confusion. So the integrals again, ty ds, right? T is equal to 2, and y is equal to negative 125. And this is a negative sign before we did anything. So what I did, I said the negative sign disappears, so this becomes a plus here, right? Makes sense. Yeah, because you have a negative here, you can just take the negative out of the integral. So then you can multiply this, 125 multiplied by 2 is 250. So you still have the ds here. So you get now from 0 to S5 of 250 ds. And since there's a constant, if you take the integral, it just becomes 250 S5. So then the question is, well, we made a cut, so we have to calculate the correction shear flow, right? So in this case, we have a special case. We can do the calculations, and if we actually do the calculations, let's see. Let's do it on this side. I want to keep this available. Okay. So let's pick a location when we take the moments around. Okay. Let's pick 0.0 because we have the shear force going to that location. So when we have, remember, this is Sy times psi, and then the moment equation, right? So this part will become 0 because there's no moment on. And then we have all the QBs, ds, QB ds, plus 2a enclosed area, QS0. So what we can say that based on looking at it, this based on symmetry, we know that there's another shear force going in that shear flow going in that direction. So if we let's plot actually draw all our shear flows. So we will have something like this. And now if you take the moments around point O, first of all, QB3, 23, 30, 60, or 06, and 76, because they all lie with they don't have a moment on, they disappear, right? Because we take the moments around this point O. So they all go through that location, so they have no moment on. If QB12 creates a counterclockwise moment, so that's positive. However, QB 87 is equal, but creates a counterclockwise moment. So these two will cancel each other out. These two will cancel each other out, and these two will cancel each other out as well. So if we go to this equation, we now have 0 because we take the shear force goes to the point of our moment origin, or the location where we take the moment around. So that one has no arm. All the open shear flows basically cancel each other out at 0. So this is 2 times the enclosed area. This cannot be 0, so therefore this must be 0. So Q is 0 in this case. Without doing any calculation, you can determine that it's equal to 0. And in many cases, you will look at this cross section. You can basically determine a very convenient point where you only have to do just one shear flow and one moment arm, or you can actually determine that it's equal to 0 without doing any calculations.
So that's why we chose the cut at 0, because it just conveniently get rid of those two.
Yeah. So by looking at it in the beginning, we could have chosen the cut at any location. So we did, regardless of any location, even if you look at it, you could have basically drawn the shear flows as is without knowing the numbers for it, then you would have noticed that if you take the cut at 0, it will cancel each other out. So you could have thinking ahead if you did it. But regardless, even if you didn't do that step, you always want to take it at a symmetry point, because then you can say, if I calculate 1, 2, 3, 4, and all that stuff, it's symmetric with respect to this axis. So always go for a symmetry plane of an axis of symmetry where you want to make the cut. And then, of course, if you remember, like the previous example we did in class, we had have a circle and with something like this, and we take the moment and we take a cut here. And again, it simplifies our life a bit, because we know we can easily find the shear flow for we can easily find the moment of inertia of a half arc circle, and we just find those shear flows easier. And then thinking ahead, also in the previous example, we knew if we have the shear flow, we want to take the moment around it, so the moment arm would always be equal to R in this case. So you can always think a bit ahead to see where it's convenient, but starting off at a symmetry plane is always the best thing to do. Okay. So I hope this is somewhat useful. I'll post a couple of online problems as well, so you guys do it, and also some book problems. So one thing I want to stress is, based on experience with this course teaching it, it helps a lot if you do the book problems. Just go through the book problems and do them. The solutions online. If you have any problems with specific problems, come to me. We can schedule a one-on-one online meeting, or in my office to discuss those. So because in this, for this course, repetition and seeing these kind of tricks is very useful. Like when I did my exam, this is a long time ago. There was one problem, and I actually have that problem somewhere on my files. But yeah, let's do two examples. I think at one point, just generic, so we got like a shear flow problem like this, and you had to calculate the shear flow back in my exam, and you were given this arc length being equal to 500. So what I did incorrectly, I started using this equation, blah, blah, and made myself way too difficult and got some incorrect answers out of it. And I'll try to find that problem, and I'll show it maybe next week, where you could have solved the same problem by just taking a summation of forces in x, y, and you would be done the same thing. So sometimes when a problem even seems difficult, but you have the experience, you know what to do before taking, say, doing a large derivation or doing a lot of intermediate step and coming to the same problem, but somewhere in between you made one mistake and you get a different value. So sometimes, and that comes with experience, and it's not something you get 1, 2, 3. It's just practice, practice, practice. So another thing, one exam, actually 1 year, I posted this exam question. So this year, this is theta, the angle between two sections. Shear force is given here. This location is xi, and the question was determine the shear center as a function of theta. So where does the shear center lie here? You see that? Yeah, this one. So what is it? Recall the definition of shear center. What is the shear center? Definition of it.
I would say it lies in that corner in between the two.
Correct. Why?
The moments are acting on the other ends, and because of that, you're going to get shear flow.
Yeah, correct. So if you remember this equation, this is an open section, so we can get rid of this part, right? So what we get is basically this. Sy times I is equal to 0, to this. This is our shear flow. Say that it goes like this and like that. So if you always take the moment on this location, the two shear flows will go through it. So this part is 0. So Sy cannot be 0 because there's a non-zero value. So psi must be equal to 0. And as a function of that, it doesn't matter what that is. So sometimes I just, and I like a lot of, first of all, I didn't give any other values than this, then, so you would have noticed that you don't have the thickness, you don't have the length, so everything. But some people would assume, like, let's assume it's T and A, and they would try to calculate moment of inertia as a function of theta, and etc. And they would waste a lot of time, but while you take it, just take a moment, look at the problem, and think about which concepts we apply. So moment, in this case, the shear center, you always know, you want to take a convenient point where all the shear flows goes through, and that comes again with experience. You would immediately see, like you correctly stated, if I take the corner point, the shear flows will go through it. So the right hand side will be 0 by definition. So therefore, psi must be equal to 0. And that again comes with experience and just doing over and over the problems. Okay. So are there any questions regarding shear flow? So we went to open sections, closed sections, and combined sections. No problem? No questions? Okay. We still have 15 minutes, so we can continue to the next topic. For that, we go back to the board. And in this case, we're going to revisit the torsion section. And now we're going to focus on torsion of thin wall structures as well. So, let me check. Okay. So torsion, we focused in the beginning. We focus on solids. So everything what we did was a solid beam. Which is a solid beam. And in shear flow, when we discussed shear flow, we went to a thin wall structure. So they had a certain thickness and the center was hollow. So what we want to do is see what the same thing is about torsion, how we can apply that to a thin walled structure as well. So this is all thick walled. This is also thick walled. Yeah. So when we say closed sections, we automatically assume and imply that it's thin walled. Otherwise, it would be a solid. So what we do is we look at again. If we want to talk about torsion and say closed sections or thin walled sections, that torsion will basically also imply shear flow. And once we know the shear flow due to the torsion, we can eventually come to shear stresses. And once we know shear stresses, we can state something about failure. Good. So what we're going to do is we're going to basically restart at the equations that we derived for the shear flow sections. And we basically say again, let's do that just off the board, on the board. So yeah. So what we do is again, revisit our shear flow equations. We stated that shear flow was Qs ds plus T times d sigma dz is equal to 0. And if you remember correctly, for torsion, we said we have a pure torsion case. We said there's no direct stresses. So sigma x, y, z is equal to 0. and we say tau xy is also equal to 0. So if we have no direct stresses, we have no sigma x, no sigma y, no sigma z. So there's the variation of sigma z with respect to z. If we have no sigma z, it basically means it's equal to 0. So for torsion, our shear flow equation becomes dq ds is equal to 0. So what does this mean? Well, this means that our shear flow as a variation of s is a constant, else we cannot get it to 0. So this means that torsion results in a constant shear flow. The shear stress, of course, can still vary. So basically, Q is equal to C, it's a constant. Shear stress was, remember, was Q times T. So this still can vary if T varies. So just keep that in mind. While we can have a constant shear flow, that does not mean that shear stress is a constant either, because we still multiply by T. So we know it's equal to it's a constant shear flow. So we still want to know what the value is eventually for that shear flow. How do we know? We now need to know a relationship between torsion and the shear flow to calculate it. So to do that, we go back to our dado shape. Okay. So we have our x-axis and y-axis. X, y. Torsion is applied somewhere. And we know that on any segments in our cross section, let's take this segment, the shear flow will be a constant. So the shear flow Qs, that will be a constant C. So, and then of course, what we have to do is we can relate the force to we can relate the shear flow to the torque by saying the same thing that we said earlier. We say if we have a ds portion, so if we do the integral of q ds, we get a shear force, and we know relationship between a torsion and a moment and a force is force equal to P is our moment, and in this case we call that just torsion because torsion is nothing else than an in-plane moment. So using this philosophy, we can come up with the same idea. So of course, we take in segment ds, we know we get a segment df, and if we want to compute the whole torsion, we basically compute the summation of all those small segments. So if we do this, we should take the integral qds. If we want to do the summation of all the forces, that's basically equal to the integral of q times p ds. Q in this case was a constant, so we get the integral of 0 p ds multiplied by q. And if you remember correctly from the correction shear flow, this integral is two times the enclosed area. So the relationship between torsion and enclosed area and the shear flow is that the torsion is equal to 2 times the enclosed area multiplied by q. So again, we draw a random shape, arbitrary shape, and we say we know the fact that the shear flow, based on this philosophy, based on this line of thinking, that the shear flow is constant. So if the shear flow is constant, if we multiply that by sigma d, delta ds, we know we get a portion of shear force, and that shear force can be equated to the torque, the in-plane moment, by just multiplying by the arm. So if you want the total torque, we need to do the moment around all those small segments around the entire cross section. So we have to do is the moment arm times ds, that integral multiplied by q. And this part is known as twice the enclosed area times q. And again, what you get is you can draw a triangle out of it. This is the moment arm P. So this triangular area, that's equal to so half times base times height. So that area is half times base, which is ds, times height, which is P. That's your dA. And if you do the summation of all the dAs, you get the full area. So if you take the half to the other side, so you get the integral of ds of PDS is equal to 2 times the area. And you can just substitute that into this equation. And then we get to this equation here, that torque is equal to 2 times the enclosed area. Let's see. I think that's a good location to stop because this next section is, so now we know our shear flow due to torsion. And if you recall correctly, another concept of torsion was important is the rate of twist and the twist angle. So the next lecture we're going to go into how we can calculate the twist angle and the rate of twist for closed section torsion. And we derive that, and that basically compensates the torsion section, and then we just do problems before the exam. Are there any questions? No? Okay, perfect. Then I'll see you guys on Thursday.